great. This is going to compare your population to your sampling distribution. Now, first time, oh, this is the tried one, sorry. You're going to try this one in a minute. Let me move this up. Here. It's still page 253. Okay, a bank auditor claims that credit card balances are normally distributed, so we know we can work with this, with a mean of 2870 and a standard deviation of 900. This comes from your population. The population of your credit card balances are normally distributed. Don't forget, this is about 10 years ago or so, probably 12 years ago now. Okay, what is the probability that a randomly selected credit card holder from the population, we randomly select someone from our population, you can, so that didn't take a minute, has a credit card balance less than 2,500. Okay. This is your population speaking here. So I'm going to do your population over here. This is the population one. Then we're going to do the sample one over here, and we're going to take a look at it. So here's your population. Here's your mean. Let's put everything out here today. So we're going to add 900 all the way up. Okay, and we're going to subtract 900 all the way down, just so that you can see the difference. $2,870. How did I get 2,500? Thank you. Let me start there. Thanks. Good thing you stopped me now. After you guys wrote it, right? Okay, put the 2,870 here. Thank you. Okay, and let's subtract 900. I'm going to need a calculator. Unless Lizzie has it ready for me. 3670.
4570.
Okay.
And 5470.
Okay, and how about if we go down?
I didn't.
Okay. And this one's 5470. And 1970 and then 1070, right?
Oh, yes.
1070 and then 170? 170. Okay, just so that you can see where this is going when we talk about your population. Now, we want the 2,500. We want somewhere right in here. And we want less than that. Okay, we want to know what the probability is that when I pull out this random person out of my population, that person's balance will be less than 2,500. So we use your z-score. And we say, okay, it's going to be negative, so smaller minus the larger over the standard deviation. And we should be able to find your z-score for this, which is negative 0.41. And that makes sense. We expected it somewhere in between the 0 and the -1. Now, we look up your area, and your area to the left is 0.3409. So we have about a 34% chance that the person that we picked has a balance less than 2,500 from our population. Okay, this is how we always did the old ones. Now, we say, okay, you randomly select 25 credit card holders. You use a sample. So you have a sample of 25. Instead of picking that one person, you're going to pick 25 of them and take the mean of that 25 and compare that mean to the 2,500 and see how you get on that. So we want to know, same thing, what is the probability that they're less than 2,500. Now, we keep the same mean, the same standard deviation. The problem is the standard deviation gets a little bit smaller. Our new standard deviation, our mean stays the same. God bless you. And our new standard deviation says take this over the square root of 25. And the square root of 25 is 5. So we divide 900 by 5. And we get a new standard deviation of 180. Now, if we go 180, and I'm going to superimpose this kind of on that graph if we could. We're going to go 180 in 3 sections. So our graph is going to shrink in. If we start with your 2870 and we add 180, we get 3050. We're over here. 3050. Then we add 180. We get 3230. We're still in here. Then we add 180. We get 3410. We're still inside of this. Look what happened to this graph. That curve came really, really narrow on us. So we kind of squished everything in. Our probability is a lot different now. When you look for your 2,500, it's going to be real close in here. It's real close in here. So now, we're going to use your z-square formula. Your sample minus your mean over your sample standard deviation. And you don't have to sign it, Jerome. I didn't take attention to that. This guy, we already know what this is because we figured it out. So we're going to take your 2,500. It still subtracts. Divided by, we're going to use your 180. And this time, we get negative 2.06. Look how much further down that is than your negative 4.1. It's way down in here somewhere. It's way down towards the end of that curve. Now when you look to the left, the probability is a lot less. So it's almost approximately a 2% chance that you're going to pick a sample of 25 and it's going to be less than 2,500. Okay, now if you look at the interpretation, maybe this will help you make sense out of this. Although there is a 34% chance that an individual, here's your individual, will have a balance of 2,500, there is only a 2% chance, this one here, that the mean of a sample of 25 will have a balance of less than 2,500. Because there is only a 2% chance that the mean of the sample of 25 will have a balance less than 2,500, that is an unusual occurrence. That is a very rare occurrence. So it is possible that your sample could be unusual. Maybe your sample is not a good representation of your population, which is why we keep doing multiple samples. And you have to decide that. Does this sample, it's only 25 out of your whole population. Did this really model my population? Did I get the right people in this to check their credit card balances? Remember how we do the plus or minus 1? That's where most of your values are. Plus or minus 2, up to the plus or minus 2, if you hit the plus or minus 2, it's unusual. If you go to plus or minus 3, they consider that very unusual. So the plus or minus 2 puts us in an unusual category. This might be a good representation of our population, or it might not. That's something now that the statistician takes a look at and sees if it's valid or not. But what's happening is you're getting a little tighter in your controls here when you use a sample. It's tightening your belt a little bit. It's not making you as sure. If it was on this end, you would have far more that would be less than the 2,500. If it was like 2,600, if it was above 2,900, let's say. If it was on the other side of the mean, you'd have far more that would be on that side. So your population comes out very different than your sample does. And it is because of this guy right here. You change the standard deviation. You divide it by the square root of n. Now remember, the larger the sample gets, if you divide by a larger number, what happens to your number? It gets smaller. So your standard deviation will get smaller and smaller, pulling your curve in tighter and tighter. Right? Not too often do we compare a population to a sample, because we do the samples for a reason, but we do compare sometimes. So now I want you guys to go to the, so if we take a look at your Z-score formula for your population, that's the normal one. You're pulling one random person out of here, or one random receiver, one sound receiver to test. And on the other side down here, you're sampling 10 receivers and using their mean, their average for the all 10 to compare. So your normal curve for your population in green here is spread out. By the time you lower your standard deviation, your curve shrinks down like this. This curve is this now, superimposed on that curve. Mm-hmm. Your lower limit has to be the negative 92. Then your upper limit. Yes.
No, I just put all the numbers.
Okay, so now that's your population one, right? So that's your population.
You plug it into the
All right, now your
standard
sample one.
deviation over the square
Bring
root
it
of
down
it.
again.
So you do you can do 150 over the square root.
Down here. And just
Square root of 5. That's to the bottom. We don't do square root of 5.
Where is 10? You have 10 in your sample.
No, I got 1.5.
Yeah, that's for your sample. Yeah. And there you go.
Yes, I was looking for. I was like trying to figure out.
Miss one.
No, you're good. This one was spread out. This one, I spread it out so you could see. I took your new standard deviation. And what I did was about 150 divided by the square root of. It's about 47. So I went 47 out, 47 down. And then I noticed it fell between these two.
We going anywhere else?
Superimposed it now it's going to be right here. I spread it out so you can see it. But if we work in this little tiny thing, you can't really see it. That's why we spread them more out.
This one.
Yes.
How do you shrink this standard deviation?
How do you shrink it? You divide it by the square root of how many is in your sample space.
Oh.
That's how you pull in it a little tighter.
Oh. And then
Okay.
and then wait, so when you do the sample, when you do the C equals X minus the mean over the do you put the new standard deviation in or
Well, either you put it in like this or you put in the new one, 47.
oh,
You don't put like
47.
point something.
Well, you can leave it at 47.
Okay.
Yeah, props, because they left theirs in all whole numbers. You could round to the whole number. I would round however they round.
Wait, so that 47 is your new standard deviation?
That's your standard deviation for your sample. That's this piece right here.
So like that's when you make the new sketch, you would use that.
Yes. So what I did, guys, if you look up here a second, here's your population in green, right? It's 150 down and up, right? Now, calculate your new standard deviation. It's 47. So I put your mean here, and I went up 47. I went down 47. So my chart went from here. It's 484 to 866. If I put it on here somewhere, 484 to 866, that's probably a little bit off. I think this is off. I think my standard deviation is off. 47. It's 766. Sorry, 766. If you look up here a second, this curve for 766, from 44 to 766, is in between 775 and 475. So your curve, this curve, actually fits right here. I just spread it out so you could use it and see, like we spread out our normal curve so you actually can write on it. If you squished it into that little space, it's going to be really hard to figure out where your 1s, 2s, and 3s are. But go by your endpoints. This is 766. So I'm a little less than 775. I'm a little bit more than 485. My entire curve fits right there using my sample standard deviation. I have to take my standard deviation and divide it by the square root of n. So let's work this through. Your z-score says take your x value, you want the 700, minus your mean over your normal standard deviation. Everything stays the same for your population. You're picking one random receiver out of your entire population. So when you do this, you get a z-score of 0.5. Yes? No? Everybody okay with that? So here's your 0.5 in green, right in here. You want all of this, the area to the left, slightly larger than 50%. You look it up in your chart, and you are 0.6915. So there's about a 69% chance that a receiver taken from your population is going to be it's going to cost less than 700. And that sounds normal, doesn't it? Because your average is 625. You're a little bit above your average. Your standard deviation is a little bit larger. 150 is a good chunk. Look where they went from. They ranged from 175 to 1075 across your plus or minus 3. That's a big spread. Remember what standard deviation means. How much something deviates from the mean. So it is deviating from your mean quite a bit. Now, we come to your samples, we say, let's randomly select 10 receivers. Then take the mean of these 10 receivers. Maybe this one costs $9.75, this one costs $2.75, this one costs $3.75. I'm going to take all 10 and I'm going to take the mean of it. It's average. It's arithmetic mean. Then I'm going to compare that to this. But when I do that, central limit theorem says take your standard deviation and divide it by the square root of how much is in your sample. You want to kind of pull this in a little tighter, okay? So it gives us a little bit more reasonableness in here. So we're going to take your square root of n. I put it over here. So it took your standard deviation and it pulled it down a little bit. And then I spread it out over here for you. But it actually fits right inside this curve in blue. Now when we do this, we keep the same thing, z-score, 700 minus 625, but we put it over your new standard deviation. Okay, it still should be positive, right? It still is going to be positive. So you're going to figure that out, and you're going to come out to 1.58. 1.58, somewhere over here somewhere. And you're going to check its area. So that area is going to be larger than the 69.15%, isn't it? It's a bigger chunk of my curve. And up here, you can kind of see you're really getting a big chunk of your curve in here. So we look it up in your table, and we get 0.9429. So there's about a 94% chance that the 10 receivers that I check have a cost less than 700. Okay, out of the sample size that we took of 10 receivers. It pulls your probabilities in a little tighter. Going on the one end, the low end, it kind of lessened it. Going on the upper end, it kind of increased it because you squished your curve in. You squished it in, you pulled it in. You pulled it in a little tighter. Does it make sense? Okay. And again, if this seems unreasonable that you end up with, you take a look at your sample. Maybe you do more samples. That's why they do sampling distributions. They keep taking samples of 10. They take the mean of the means. Because maybe one sample isn't going to cut it. So you do this again and again. And you